Morning. Welcome to the Texas Instruments Australia webinar series. Today's webinar is Mathematical Methods 2016 and Beyond. My name is Rodney Anderson and I'm the host for the webinar. The webinar will be presented by Peter Flynn and Russell Brown. They are very extremely knowledgeable and very experienced presenters. This webinar is being recorded and will be available on demand on the Texas Instruments Australia website. If you have any questions during the webinar, move your cursor to the middle at the top of the screen. Select questions and answers in the floating menu, type your question and send to all panellists. At the conclusion of the webinar, an email will be sent to you in a few days and it will also include your webinar certificate and links to resources. The first presenter will be Peter Flynn. Welcome, Peter, and we are looking forward to the presentation.
Good afternoon, everybody. Thank you for listening and watching. Hopefully you can see my desktop. What Russell and I are going to do this afternoon is have a bit of a look at Mathematical Methods 2016 and beyond. There's quite a bit of territory to cover, so we'll just pick out a couple of topics that are new and hopefully do them in some depth. If we first of all look at Units 1 and 2, VCE Mathematical Methods, Russell and I both need to make a disclaimer that we have no affiliation with the VCAA, and so therefore any technical questions relating to syllabus coverage should be directed to them. I've had a quick look at the study design for next year and I've pulled out some highlights that I will note here. I may have missed something because I would have had a boy's look. So the onus is on you to make sure that you know exactly what's being covered. Russell and I aren't to be blamed for anything. So in Units 1 and 2, absolute value functions have been moved to specialist mathematics. There appears to be a less of an emphasis on matrices, although they're still needed for transformations. Markov sequences have gone. The rational root theorem has been added to one of the dot points in Unit 1 algebra. The bisection method has been included, which allows us to find approximate solutions to equations. We may not have much time today to go through the bisection method. We will if there's some time at the end, but essentially it's a foolproof method for solving equations where you continually halve the interval. It works, but the convergence of it is extremely slow, and you need quite a number of iterations to be able to solve, to be able to narrow the interval down so that you'll be able to say that the root lies, say within 3 decimal places of the endpoints. Informal consideration of sample proportions, so we'll show you how to do some simulation, and Russell will also take you through an application of differential calculus, which is an iterative method called Newton's method for solving equations, and in the study design it's specified to be cubic polynomial equations. So Russell will go through that, and then we might just now tap into Unit 1 and 2 first of all, and then after Russell talks about Newton's method we'll come back and have a look at Units 3 and 4, because there's an area of study there, probability and statistics, which is vastly different to what the previous or the last year of the Math Methods course, big changes on offer for next year. So if we have a look at Unit 1, there's some changes in emphases here, so I've just pulled these out. These are courtesy of the study design. The use of the vertical line test to determine whether a relation is a function or not, so the general vertical line x equals k, and also the parabola x equals ay squared have been specifically mentioned. The second dot point, I've pulled that out because I think the powers of n have been widened there. Graphs of inverse functions are required. That second last dot point includes the remainder, factor and rational root theorem, so that's where the rational root theorem is mentioned. and also the last dot point has been isolated and put on this slide because it mentions using the bisection method to solve simple polynomial equations. My reading of the study design is always that long division is not mentioned in the study design, so it always amuses me that you all teach something that's not on the syllabus. Okay, we have a look briefly at Units 3 and 4, just in terms of changes. Really the biggest changes are, again, no functions involving absolute value. There's no matrices except for transformations. Related rates of change, I believe, have moved to specialist mathematics. There's no double or compound angle formula. They've been moved to specialist mathematics. Although when you use a CAS and with the auto simplification function power of the CAS, there will be times when students stumble upon trig expressions whereby you might need to use a double angle formula or a compound angle formula to change its appearance. So it's an interesting dot point, that one. Markov chains have gone, but the big change really is that as well as the probability that's already there, there's quite a sizable statistics component has been added, in particular sampling and estimation and dealing with the sampling distribution of sample proportions. So the last half of the webinar will be devoted really to that dot point there. So what I might do to start off with is to just show you a couple of tips and tricks which relate to Unit 1. And the first thing I would like to show you is how to graph a vertical line, which can be used to determine whether a relation is a function or not. And so one approach for graphing a vertical line is to press menu, and then I don't really like this. I prefer this to be graph mode because I want to change the graph mode. I don't like graph entry edit as a name. And we're currently in function mode, but what I would like to do is I'd like to change it to equation mode. So I can press 2, and then if I want a line, I can press 1, and then if I want a vertical line, I can press 2. And the vertical line template appears. Then it's just a matter of typing in, let's say we want to graph the vertical line x equals 3. We press 3 and we press enter, and there is the vertical line. Now I also would like to show you an approach to graphing that not many people might be aware of. That I broke the world record for going through various sub-menus to dig out that command, but you can actually graph like this without going into the menus, and that is done by making use of a text box. So if you move your pointer, and can I say at this stage that for some parts of this webinar you will be able to follow what we're doing just in terms of pace, but there will be other times where we'll be demonstrating with prepared files, and there's no way that you'll be able to construct the files and then stick with us. But what is the case is that you can replay this webinar again, stop and start, and develop the skills by watching the webinar over more than an hour and a half. So with my pointer here in open space, if I press on the handheld, it's control menu. I'm working on a PC at the moment, and I did a right click. Control menu and right click correspond to what's called a contextualized menu. And what I want to do is I want to press number 5 to open up a text box, which I've done here. And what I'm going to do is I'm going to graph, or attempt to graph, a member of the family of curves x equals ay squared. So let's type in x equals 2y squared. I'm using a borrowed computer, so I don't know where anything is. And then press enter. Notice also that I didn't use the multiplication sign. Implicit multiplication is recognised here. So I press enter, and what I do then is I take my text box and I move it up to make contact with one of the axes, press enter, and there we have the graph of x equals 2y squared, and you can interact with that as well. You can change the dilation factor. And so what you can do there is you can talk about the fact that x equals 0.27 y squared. How does it sit with regards to the vertical line test? Is it a function, for example? So that's a trick that you can perform with graphing. If you wanted to graph x equals 2y squared from the menus, you press menu and then graph entry edit, so press number 3, number 2 for equation, number 2 for parabola, and then the vertex form that you are after is number 3. And so therefore what you would do is you would fill out that template and you would be able to graph the function, well, the relation x equals 2y squared. Okay, so we might press escape there, and I might insert now another graph page. So one way to insert a page is Control I, and the I stands for insert. Another way to do it is to press, if you've got a CX, is Control Dock to add a page. And so if we add a graphs page, press number 2, we have F1 of x. Now, what I'm going to do is I'm going to show you how to graph a function and its inverse using, for the latter half, this text box approach. So in this page here, what we might do is we will graph the function f1 of x is equal to e to the x. So if we press the e to the x button and then press x and then press enter, then what we should get is the graph of the natural exponent function. Very interesting here that while I'm by myself here in Kyneton, I have been informed by my colleague that we're on quite a bit of a delay here, so apologies if the instructions and what you're seeing on the screen are not quite in sync. I am cognizant of it now, and I'll try my best to slow down and anticipate it. Okay, so no real need to change the window here. Move the pointer off into, don't make contact with the axes, be in open space somewhere, and then control menu or a right click on the PC, control menu or a right click on the PC, then select 5 for text, and then in the math box here, now if we want to graph the inverse, the relationship between a function and its inverse really is a swapping of its coordinates. So the point xy becomes the point yx. So we look at this and we say, well, what would happen if we graphed x equals f1 of y? Let's see what would happen there. So inside the text box, if we press x equals f1 and then open bracket y and then press enter, of course the first part of this demonstration is always a bit deflating because nothing happens, but then what you need to do is you need to grab that text and move it till it makes contact with the axes. Now, I neglected to say this the first time. I'm assuming that everybody knows how to grab and move. What you would do here, you've got your click grab button and the hand is in blue, and so I can't demonstrate this on a computer, but what you would do is you would press and hold down on that click grab button for 2 seconds until that hand, which is currently open at the moment, would then close on the handheld, and then you can move it. But all I need to do is press down, or left click really, and just use my finger to move it, hits the axes, bang. And I wonder what we've graphed there. Well, we know that that function there is the graph of the natural log of x. All right, so they're inverse pairs. And so that's a nice simple way to graph an inverse function on the graphs page by making use of a text box, which seems incongruous, but it works actually quite well. And then, of course, you could press tab to open up the entry line, and you could type in y equals x for a very good reason, and then you can discuss the symmetrical relationship between the natural log function and the natural exponent function. So that's quite a simple demo that you can use. You could put points on the curve and show that x, y and y, x, etc., etc. But we haven't got the time to go through that today. The final trick that I need to show you before looking at some new mathematics is in version 3.9, the command bounded area was introduced. And so to insert a graphs page, this time I might press Control Dock. And Control Dock is another way of adding a page. This follows the Bill Gates rule of 3. I've shown you two ways to insert a page. So we're going to add a graphs page, so you press number 2. And what we're going to do here is we're going to graph two functions and then determine the bounded area between the graphs of those two functions. In other words, the area between two curves. And so I'm happy with f3 of x, that's no problems. And so what we might do is we might go with x squared, and then we might multiply that by e to the negative x divided by 2, and then press enter. And then I'm just going to move that label down a bit. Again, I'm not going to be too worried about the window here. You should be able to see what's going on. To bring the entry line up again, we press tab, and for f4 of x, I'm going to choose to graph 1 minus sine, which you can just get from the keypad or from the trig button there, open bracket x divided by 2, and then press enter. So we've got these two curves here. Now, traditionally, examination questions of this ilk would be, consider the functions f of x equals blah and g of x equals blah. Part A would be find the points of intersection between the two curves, and part B would be hence find the area between the two curves. Well, you can do the questions now in reverse. You can actually find the area between the two curves really without finding what the points of intersection coordinates actually are. And so what we do here is we press menu, and then we go to analyze graph number 6, and then bounded area is the command that we're after, so that is number 8. And then what you do on a handheld, you will use the navigation pad, that great big button, and you will move this lower bound. You will move this lower bound towards the point of intersection, and rather than stick with that vertical line, actually move up and make sure that your pointer makes contact with the intersection point, like I've done here. I just missed it, Hang on, I'll just press escape and just try that again. Make contact there, intersection point, and then click on that. Go to the second intersection point. It's telling me that I've made contact with it, and I click on that. And so note, folks, that you have the bounded area, which is 8.28 square units, but you don't have the coordinates. Well, it would be a matter of just making contact with the point And then again, it's this contextualized menu. It's control menu or a right click on the PC to get coordinates and equations, and you could get those one at a time if you wanted or if you needed to calculate the x coordinates of the intersection points.
Now, Peter, they may be asked to find that to
Russell, where did you come from?
to 3 decimal places. Can you just put the cursor over the 8.28?
Trust me, I have.
And hit the plus key. There is a big delay. Is yours moving?
Thank you, Russell. Russell's just dropped in. He's come along with a suitcase. He looks homeless, so I think he's been kicked out of home. And he's arrived in Kyneton to help me with the webinar. So thanks very much for that, Russell. And just one other thing to note there is, yes, we could find that second intersection point in the same manner. I like Russell's approach of putting the cursor on the x coordinate there, and you can change the how many decimal points, how many digits you see after the decimal point. So that's all quite good. In 4.0, there's also the bounded area with regards to the x-axis. The x-axis is considered the second curve. So if we add another page, and we add a graphs page, and if I type in x squared minus 5x and press enter there, if we now go to menu and then number 6 for analyze graph and then number 8 for bounded area, there's a prompt that will appear at the bottom of the screen. Which graph are you talking about? So I'll move my pointer over and click on that parabola, and then it asks me for the second graph, so I'm going to click on the x-axis, and then it's asking me for a lower bound. So I'll make sure that that intersection point, so that's x equals 0, that's the origin, so I'll click on that. And then if I move across, notice that that bounded area value that's growing as I move that vertical line, it's positive. It's positive. So even if I go to say x equals 6 and click on that and then move this label, you can see that the bounded area there is, in exact terms, it's actually 71 on 3 square units. It's 23.7. So that feature is new to 4.0. So if you have 3.9, you don't have that feature. And so it is worthwhile, to the best of your ability, keeping up to date with the updates. As the updates continue on these days, the changes are really becoming quite minimal. There's not that much change at all, but you just never know. There might be a nugget there that might help your students in the exam. So look, with that now, just doing a few tips and tricks, I'm now going to pass over to Russell, and Russell, who's looking quite dishevelled looking, he does look homeless, he's going to take us through Newton's method now, which is new to Unit 2. So he's going to look at it from the point of view of a conceptual basis, but also how well Nspire will enable us to automate Newton's method. So it's over to Russell.
Thanks, Peter. Hopefully my screen is moved over to my computer and all can be seen by our viewers. Now, it mentions Newton's solving with cubics, so I've decided to just do a quadratic, just to be different. Obviously the same thing. They will give you a starting point, or it doesn't really matter whether they do give you a starting point, but you'll have to just go for a single root value. So the cubics that would be given to you probably would just have one root value. So that was one of the reasons why they would choose, say, a cubic over a quadratic. But we'll just have a look at the root value on the right-hand side. I'm just going to show you very quickly how it works, just doing a construction. Now, if you do have your calculator handy, your computer is a little bit difficult to be using because you're watching us, but if you have another computer with the software on or the handheld, you may just want to do just one of these and then finish it off later. So basically all I've done is put in a function x squared take 3, and we know what this root value is, so we can remember all of these from our early days of teaching, what root 3 is equal to, the positive root 3. So all I've done is I've constructed a perpendicular on the x-axis, but I've made sure that I didn't go on one of the tick marks, because I'm going to grab this point later and just move it along here, because I want to see how the tangent changes. So what I've got here is the perpendicular line. If it's not quite long enough, just drag it, just grab the end of it and drag it up so it cuts the graph. And we're now going to go to my menu and just go to Geometry, Points and Lines. I know there is a slight delay. Being here in the country, we try not to be too far behind. And we're not Queensland either, Rodney.
No, we're even further away, aren't we?
So you should be able to keep up. So you should be actually seeing what I'm doing ahead of when I'm doing it.
Yeah, should, but I thought you used the TARDIS to get to Peter's place.
Okay. So I'm going to choose tangent, because basically what Newton's method is based on is we take a starting value and a starting x value and look at its y component, the y ordinate, and draw a tangent at that point. So I'm choosing tangent from the points and lines, and I'll move up to intersection points. Peter just showed you that we actually don't have to find intersection points in a lot of cases. It will automatically identify it for us. So I'm going to draw a tangent there, and I'm just going to grab the end of that tangent. I just need to press escape because I don't want to do another tangent. And you can see that it's cutting through the x-axis at that point. So there's the equation to the tangent, not important, so I'm going to right-click on that, so that's like a right mouse click, and I'm going to hide that. Don't delete it, because that will delete your tangent as well.
Russell, just it's still coming on the screen. Oh, there it is now. Yeah, it's a little bit delayed.
Okay, yeah, I'll just try and hold up a little bit here. It's a very, very quick iterative process, this one, compared to the bisection method, but it still takes a while to come up on the screen. Now, what we're going to do is we're going to look at where this cuts the x-axis now and draw a perpendicular at that point. So I'll just go to my geometry, points and lines, and do a perpendicular through that intersection point and perpendicular to the x-axis. So I click on the point and then click on the x-axis, and basically what I've got to do now is draw another tangent at that point there. So basically we're just using an iterative process of finding where the tangent cuts the x-axis, use that to create the new tangents, and just continue until we hone in on the root value. And it is a very, very quick process. So I'll just do one more here. So there's the tangent at that intersection point, and you can see already we're pretty well at that root value. I'm going to hide this equation. Yep. I'm hearing there's a slight delay, so it's pretty hard to guesstimate the delay. So I'm going to grab this point now, and I'm just going to move it back a little bit. And if I keep moving this, you can see all of those tangents hone in to this root value there. So there it is showing there. Now I can, if I wish, find the coordinates of that point. So there's the coordinates of that point. The root value, I'm actually just going to go to Analyze Graph and do a 0 on that graph between there and there. So there's the actual root value there, and I'll just put my hand on top of that and just hit the plus key, and I'll just increase it a little bit. Now, we could go to our settings and change our display digits. So by default it says float 3. We could set that to anything, including auto, which would follow your general settings from the main page. My suggestion would be is just leave it as float 3 and just do what I've done there. Ones that you do require a larger value for, just place the cursor over that and hit the plus key. If it doesn't increase it, it may well be that the next digit is a 0, a trailing 0. And if you hit the plus key again, it may then just put, say, a 2. So the last 2 digits would have been 0, 2. And so we know that is the actual root value. So if I now just keep dragging that point, you'll see that point is the one that I'm dragging. As it comes in there, it will hone in to basically that value. So you can see that we've got a very, very nice method. So that is called Newton's method. Now there is some very, very interesting little things here with the derivation of this. As I said, I've just chosen a quadratic because it is easier to do just a little bit of mathematics on it. Just a little bit more simple to do that. So hopefully that's come up on your screen or not.
Yes, it is now.
A very, very slow thing. Very, very slow iterative process on these computers in the bush. We can't rely on our ex or our current Prime Minister to fix up the NBN anymore. He's not there yet. Okay, let's take our function x squared take 3. Now, this is probably worth going through with your students why or how the iterative process works. And it actually is quite good because it covers linear equation, just forming linear equations. Also does a little bit of calculus, the meaning of the gradients of the tangents. So there's a lot of mathematics that it ties together. So let's just take our original point, which I'm going to call x0. So that was the first point that my perpendicular touched the plot. So that was the first point we had, and I'm just going to refer to that as x0. So using our y take y1 equals m x take x1 rule, and they all should have done that by now, back in year 9, year 10, and now in year 11. So the y take y1, the y1 is just going to be f of that initial x value. So that's f of x. That's now going to equal the m value, which is the derivative, the gradient of the tangent at that point, x. And the next part is x take that x value. So the y and the x there are the part of the new equation. So what we need to do is, once we've got that equation, that's the equation there of our tangent, we need to know what that x value is of that tangent when it crosses the axis. In other words, when y equals 0. So we're just going to rearrange that, and once again, don't need to do it on the calculator. If you wish, you can. So the new x value, and I've just called it x. Of course, we refer to that as xn plus 1 if you're looking closely at the study design, equals our original x, which I've just called x0, but more generally we call that xn, minus, so all I've done is rearranged that graph, just made it equal to 0, that tangent line, and just rearranged it. So we end up with f of x0 all over the derivative of x0 of that equation, of that tangent. So that's equation or formula that they see there. They can actually be shown and led through that, and some of your brighter students probably won't need to be led too much through that to actually get it. So what I'll do now is, if we just look at this one here, remember this was the equation f of x equals x squared take 3. So I'm just going to say that x0 and my starting x was a 1. So put that into the equation and we will just go through and solve that, and it should work out quite nicely for us. And I've just got that working through there nicely. And the only thing we need to do is, if we want to do this on the calculator, once again, not too difficult to do. Hopefully that's showing all right on your screen just at the moment. I've just scrolled down. It's slowly getting there. So what I'm looking at here now is the case that we chose was x squared take 3. Let's just say the x is a, rather than x0, something like that. We'll just call it a. So I'm going to define this new function, which is basically where it's cutting that line. So g of a equals my original x minus the a squared take 3, so that's the x squared take 3 bit from the function, over the gradient. So we look at the gradient f dash of x, it would be 2x, but x is a, hence we've got the 2a. So that's now my new function that I'm going to use for my iterative process for newtons. So let's just say the original point was 1. So I put in g of 1 and the answer comes out as 2. Now if you look very carefully here on that line, after that 1 I've put a decimal point in. That's because with the method students we will probably have the default setting on radian and, on auto, which would give us exact answers all the time, and a little bit we really want to look at root values as decimals, so I'm just forcing it into a decimal there. Now the next important thing is that our new value, our new x value where it cuts the x-axis is 2. I'm now just going to put g of the answer. I cannot type in 2 because I want to set up an iterative process. So I'm going to say always look at the answer, the previous answer, and put it in there. And then when I go pressing enter, 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 you can see that I'm coming very, very close to the root value. So if we look at Newton's method here, so there's our specific case. So if I put in g now of 1 point, so there it is there. So I'm just saying my a is a 1, that was my starting point. It could be any value. I could start at 5, 6. It hones in very, very quickly. So there's that value there. Now I'm just going to say g of that answer. Now I'm just typing in a and s. I can pick it up from control and the negate sign. So there's the next solution. Because my previous line was g of the answer, if I press enter again, it will be g of the previous answer, and we're just going to keep doing our iterations, and of course we know root 3 is 1.732 plus whatever. So you can see that it's honed into that value very, very quickly. So that's basically Newton's method, a very, very nice little approach, and once again here it is as the dynamic one that we created earlier on. You can just see. Again, I'll slow down my dragging a bit so you're all on board. So there's my answer there. And look at this, if I keep dragging across, I can actually pick up the other root value. But in the study design, it will be a cubic, more than likely just with one root value. So you won't have the fun of showing off to your students all your skills that you've created there. Now, Peter, I think that should be enough, not unless you wish to talk a little bit more on Newton's, but you may want to go on to probability.
I will talk about Newton's a little bit, so if you could show my desktop a couple of minutes on Newton's method and then the remainder of the session on probability.
And there's no questions so far. Maybe you're doing such a great job, there's no questions.
You shouldn't have said that, because now there'll be a question.
There'll be lots of questions now. I'm hoping to get some questions.
Rodney, can you see my desktop?
Certainly can, Peter.
Thank you. Okay, so just very briefly, I've got a very busy page set up here. So this is, again, an alternative to Russell's dynamic approach. And so what we've got is I've got the graph of a cubic. It's negative x cubed plus 5x squared minus 3x plus 4. And then what I can do is if I go into the way to move around active parts of a screen that are different applications, this one's currently active because it's got a bold border around it. If I wanted to make the graph page active, I'd press Control Tab. And then if I wanted this notes page down here active, I would press Control Tab. So that Control Tab is occurring in a clockwise manner. So Control Tab again. What I'm going to do is I'm going to click on this clicker and let's see what happens. Our initial guess is 3.6, x equals, or x naught is 3.6. And look at that, right? So we draw a tangent to the curve at x equals 3.6. Then that tangent cuts the x-axis at x equals 5.53. Right, so here we see the iterative process. We then draw the tangent to the curve at x equals 5.53. It cuts the x-axis at x equals 4.799. And then we expect to see a schmozzle occur as n increases. So in general, Newton's method is pretty fast with convergence. You can do some high-powered maths involving Lagrange's remainder theorem and Taylor's power series work. And what you'll find is that the convergence is roughly quadratic, which means that the digits tend to become accurate. They double in accuracy each time you do an iteration. But there are some problems with Newton's method. It doesn't always work, and sometimes if you don't choose the right starting value, you could end up doing hundreds and hundreds of iterations. And there's sometimes where you'll never be able to get an answer, which I'll show you just in a moment. So here what I've done is, I'll come back to the problems just in a moment, but here what I'm going to illustrate is Newton's method and a spreadsheet approach. And I've set up a notes page here. I don't know whether you've seen a notes page or not. So I've got some text there. This is what's called a math box, and I'll show you how to insert one in a moment. And what I've done is I've assigned f of x to be this cubic, and assign is accessed by pressing Control and the symbols template. Assign works the same way as define. If you've got a fair few dopey students in your class, I'd probably tend to use define, because the dopey students, when they come to assign, use the equal sign rather than the colon equals. Then we've got, I use dopey in a playful way. F prime of x, we can't use f dashed of x, so we assign that to be the derivative, and then I've set up another math box here and typed in f prime, and that's the derivative, and that's my initial guess. My initial guess has been assigned to be 3.6. From that graph, actually, I could have assigned the initial guess to be a lot closer. I wanted to start a little bit further away so you could see the tangent process occur. If you start too close, you know, you'd have to really zoom in to see what's going on. So if I go down here and I press enter, I'm not going to wreck this page, but to insert a math box, what you can do is you can press menu, and then if you want to insert something, number 3 for insert, and you want to insert a math box, and if you have a look at the shortcut there next to the math box, it says Control M. So Control M is another way of inserting a math box. So if I press 1 or enter, so I've got a math box here, and for example, if I wanted to type in, let's say, F, notice that it's bold and non-italicized, open bracket X. You wouldn't believe that the two boys are doing this presentation, because we're both looking at 2 computer screens just to try and ascertain the delay. We press, and boys can only do one thing at once. We press enter here, and notice that it's picked up on f of x being negative x cubed plus 5x squared minus 3x plus 4. If I went back up into this top math box and I changed this to negative 2x cubed, etc., etc., and then pressed enter, notice that you get an update for the derivative, and obviously f of x is updated. So these are dynamic and interactive. And in fact, if you set them up and use them properly, which would be a talk for, or a webinar for another day, my feeling is that students should gain 10 or 12 marks in the exam 2, extended response, without knowing any mathematics. Actually, they'd even be able to get a few parts into the Tasmania Jones question. So we go back and we change negative 2x cubed to negative x cubed and press enter. So that's all right again. And the reason for setting this up is if we go to the next page, I've set up a spreadsheet which illustrates Newton's method. Notice first of all that the column headings, n for the number of iterations, xn, which is a particular guess, f of xn is the function's value at that guess, and f prime of xn is the value of the derivative at x equals xn. And notice, you just see underneath my pointer there, it's suggesting that I've used an underscore. Now, underscore is obtained by pressing Control space. You can't, for column headings, use brackets. That's why it's f prime xn with that underscore. So if we go into, this is called a formula cell, and formula cells are where you write formulas. And so I've set up a sequence, and this goes for n values from, now I've chosen arbitrarily from 0 to 8. You might need more iterations possibly. So I've just used the keypad here and just typed in here SEQ, which stands for sequence. You've got to give the sequence a name, so I've given it the name K. It wouldn't be a good idea to call it N. You would end up with a circular definition. Then we say that we're going to construct or work out this sequence with respect to K. Our starting value is 0. Our finishing value is 8. If you wanted to just go up in consecutive integers, you don't need the comma 1. I've just got that there for completeness, and therefore that's how you get your n values. Now if you go into cell B1, sounds like we're going into Pentridge, into cell B1, notice that in this entry line here I've actually typed in equals x0, and that was defined on my notes page on the previous page. We've got continuity and interactivity between the two pages. So in there I just typed in equals x0 and out comes 3.6. If x0 on the previous page was 2, a 2 would appear there. Here I'm just appealing now, what I know about spreadsheeting can be written on the back of a postage stamp, but I know that in here I can type in equals f of b1, and that will give me the function value for when we have b1 as 3.6. And then in cell D1, this is obviously f prime of b1. And so then it's just a matter of doing some fill down. And so if we go into cell B2, you can see that the similarity here with Newton's iterative scheme, that it's equal to get B2, it's equal to our B1, or our x value, minus the function value at that x value divided by the gradient or derivative value at that x value. And then it's just a matter of filling down. So to fill down, you would press menu and then data number 3, and then fill number 3. And then if you wanted to press arrow down, and you can arrow down as long as you like, for as far as you like, and that's how you fill down. Okay, so that's the spreadsheet approach. You can also be very, very crafty. Here's another notes page approach. And can I suggest that these made-up notes pages, as I said a couple of minutes ago, they can be constructed and taken into exams. There's no restrictions there. So here I've got my x0, here I've got my Newton's iterative scheme, and if you wanted to perform 6 iterations, you could set this up like this. If you wanted 8 iterations, you'd have 8 Gs. If you wanted 4 iterations, you could have 4 Gs. So there's a smarty pants way of doing Newton's method. And finally, I think it's really important with the students that you discuss that Newton's method is not infallible in double negative. It's actually fallible in particular circumstances. Sometimes you'll get an oscillating sequence or an infinite cycle of values, for example, and we'll show this with you in a moment, where you've got that cubic and that starting value. You just end up in this infinite loop that you can't get out of. And of course, if you know the geometry of Newton's method and you know the behaviour of cubics, it would be folly to start at a stationary point, because the tangent to the curve at a stationary point will be parallel to the x-axis. And it would be really nice to talk to the students about the fact that that corresponds in Newton's formula to a division by 0. So you can see mathematical, geometrical and graphical reasons for why Newton's method breaks down. So if I take us back to this fancy page here, 1.3, and I press Control-Tab to activate the graph screen, and then I press Tab to activate the entry line, and then if I go up here, I must stop because we're now on possibly one of the longest delays ever, I've just been informed.
Yeah, it's a bit delayed. I think might be working on the NBN, are they, down there?
Rodney, just keep peddling, for God's sakes.
Okay, I'll keep peddling.
Okay, so apologies for that. All I was doing was I was just moving pages. I haven't done anything. I've just moved from page 2.4, I think, to 1.3. So now, moving here, what happens if I press Control? Right. Control 1, rather than hitting the right arrow key and going, I can just press Control 1, and that will take me to the end of the entry line. If I press Control 7, it takes me to the start of the entry line. No more. Can't believe I've just done that in a webinar. So what I've just done here now is I'm going to change this to x cubed minus 2x plus 2, which I believe is my problematic cubic. So I've just entered that. The stop and go man has just told me to hold fire.
While you're waiting, you could probably talk about how people could change the
I'm
colour
just
of your graph.
Russell actually that he just logs out and turns off because the delay is becoming quite problematic. Which means I won't be able to see now whether there's a delay or not, Rodney. So if you can help me out there, mate.
It's still sitting at the end of 2. That's all. Just waiting.
Yep. So now if I press Enter, and what you should see is a new cubic.
Yes.
And then I'm going to press Control-Tab, and it's going to take me around, and I'm going to change this initial guess, which is a math box. I'm going to change it to from 3.6 to 0, and press Enter. And so what I'm going to show you now is what happens. When we press Control-Tab and go up to our clicker, notice that our value, you've got this oscillating cycle, that the guesses just oscillate between 0 and 1. So at x equals 0, the equation of the tangent is y equals 2 minus 2x, and that cuts the x-axis at x equals 1, and at x equals 1, the equation of the tangent is y equals x, and the x-intercept there is x equals 0. So that's illustrating that Newton's method is fallible, and it's worthwhile showing the students that. Is that pace all right now, Rodney, just in terms of the delay?
That's good pace there. Yeah, that's good.
Oh, yeah, I've kicked Russell out. He's got to go and find another home. So we're now going to move on and have a look at, for the last 35 minutes of the webinar, we're going to have a look at some probability. And so the first point is, let's have a look at the study design and get a bit of a handle upon what you're expected to teach. My feeling is that most teachers can teach algebra and calculus reasonably well. I think to teach stats well, I think that you have to work at it. It's not an easy art form. And so what's been introduced into the study design is quite a large component of statistical inference. And what that means is you're looking at samples and you're looking at sample statistics, for example, mean and variance or mean and standard deviation of a sample or samples of a particular sample size, and then you're going to be making some inferences, or you're going to be inferring something about the population given what you see in the statistics of the samples. So you've got to make the distinction between a population parameter and a sample statistic. So you've got, for math methods, you've got a population proportion and you've got a sample proportion. You've got a population variance and also a sample a variance or sample standard deviation. And we use the sample statistics to estimate the population parameter. And the thing is that these estimators, that's what they're called, have to be unbiased. If they are biased, then they're not worth using. What we're going to look at is we're going to look at the concept of what's called a sample proportion. Capital P hat is a random variable. And where students are going to get really confused, and here is the following. Capital P hat is a random variable. Little p hat is a sample proportion, and little p is a population proportion. And notice that this sample proportion, capital P hat, consists of, or is equal to, a random variable capital X, which happens to be a binomial or binomially distributed random variable, divided by n, which is the sample size. And random variable capital X, x will be the little x will be the number of successes, and then obviously n minus x will be the number of failures, and success will be a particular attribute. It might be eye colour, it might be right-handedness, etc., etc. So we're dealing with populations that consist of two types, really. Then what you need to be able to demonstrate to students is that as you increase the sample size, the distribution of the sample proportions starts to behave more and more like a normal distribution. So you need to be able to demonstrate that. You can't just tell them that, because the students will just say, huh? You've got to show them. And for such situations, the mean is P, which is the population proportion, and the standard deviation is given by the square root of P by 1 minus P all over N. And it's really important that students know where that N is, because you increase the sample size, and what should happen is you should get sample proportions that are less spread out. There's less spread. You need to be able to demonstrate simulation of random sampling for a variety of values of P and for a range of sample sizes to illustrate the distribution of this random variable P hat, capital P hat. You also need to demonstrate to students that from a large sample, the population proportion little p, there is what's called an approximate confidence interval, of which we often use a 95% confidence interval, where the population proportion P lies between, and it's approximate because what we do is we replace the population proportion P, we see how we replace that population proportion with our best estimate, the unbiased estimate, which is the sample proportion P hat. So that is why that's called approximate, because of that substitution. So the population proportion lies between P hat minus Z, which is a typical Z value from a normal distribution, multiplied by that quantity, and then the upper value is obviously P hat plus Z times that quantity. Z's the appropriate quantile for the standard normal distribution. Most of the time students will deal with the 95% confidence interval as an example, and Z is approximately equal to 1.96. If you go and have a look at it on your calculator, it might be something like 1.9599. It's really, really close. And note that the term standard error may be used, but also is not required. So having made a couple of remarks about having to be quite artful in teaching statistics, you're going to have to be even more artful when it comes to the derivation. Now, I don't think you can shy away from derivations. You know, why is the mean of the sample proportions, why does it end up mirroring the population proportion as the sample size gets bigger? Why can we use it when we're looking at sample statistics and inferring attributes about a particular attribute about the population? Well, first of all, what we can say here is we can say that the mean of the sample proportions, capital P hat, is equal to capital X on N. So we've already discussed what they represent. Then if you use some expectation algebra, the mean of the, so E of P is the mean of the sample proportions. E of P hat is equal to E of X on N. And using expectation algebra, in other words, using the result that E of AX plus B equals AEX plus B, what happens is that the 1 on N comes out the front, and so you get 1 on N times E of X. That's the expected value of X. Now, where you have to be quite artful is I've had a boys look in the mathematical method study design for 2016, and I don't see expectation algebra in there. Where do I see it? I see it in specialist mathematics. I'll leave that there for the time being. Knowing that the mean of a binomially distributed variable is equal to the product of N and P, we can replace E of X with NP. The N's cancel, and so therefore this is the foundation or the basis for which we can infer what's going on in the population from the sample. The mean of the sample proportions equals the population mean. And then if we look at the corresponding development for variance, the variance for the sample proportions, capital P hat, is equal to the variance of random variable capital X divided by N. Now we also need to make use of expectation algebra, which I don't see in math methods in 2016, I see it in specialist maths, is that var of AX plus B is equal to A squared times the var of X. Makes sense that it's A squared because you can't have a negative variance. You then bring out the 1 on N squared out the front. The variance for random variable capital X, if random variable capital X is a binomially distributed variable, is the product of NPQ. Q is 1 minus P, so it becomes NP times 1 minus P, and then an N with one of these N's cancel, and that becomes the variance for the sample proportions. P times 1 minus P all over N. Now, I really think that you have to show the students this, and I'm cognizant of the fact that they'll find it difficult to understand, but with some decent simulations and teaching in a manner which I call dynamic statistics, you might have half a chance of getting them to understand these results. And that's going to frame the remainder of the webinar, is to have a look at how can we bring this quite dry formal mathematics, how can we bring it alive? And so we have to start the wrong way around, unfortunately, is what happens when we take samples is we want to, when we undertake random sampling, we want to understand something about the population. Now, to do this, we have to go the wrong way around, and we've got to, in this instance, we've got to assume that we know something about the population. So we're assuming that 67% of people in Victoria are considered to be right-handed. So when you teach this from the start, make sure that the students understand that the overwhelming majority of the time, P, the population proportion, is unknown. But we have to cook this example up to see the relationship between the sampling proportions, the sample proportions, and the population proportion. And so the question here is, generate a possible distribution of sample proportions that may be obtained when 200 different samples of size 10 are randomly selected from the population. And then we're going to repeat this one again for n equals 30. So n represents sample size, so we're going to increase the sample size here. And then what do you notice? So here's, when we used to teach geometry, we used to teach it in a static manner. Nothing ever moved. Then with dynamic geometry software, we could make things move. We could see that the sum of the three angles of a triangle is 180 degrees. Sum of the opposite angles of a cyclic quadrilateral are 180 degrees, etc., etc. No matter what you did with the triangle or the cyclic quadrilateral. Well, what we can do is we can start doing some simulations with Nspire, and we can see what happens, what is the behaviour of the sampling proportions, and how does that relate to the population proportion. So if we go to the next page, this next page will need a couple of minutes to explain its architecture. It's a split page, and the left-hand side of it is a list and spreadsheet page. And in column A heading cell, I've called it prop RH, just to consider that we're talking about the proportion of right-handers. Then we have a formula cell. Now this formula cell is constructed using, well, I've used a formula, and the formula consists of a random generator command called a randbin. A random binomial generator. So what it does is it generates a series of zeros or ones. And what we can do is we can treat 1 to be a success, 0 to be a failure. We can then add up the number of successes in a sample and then divide by the sample size to get a sample proportion. So the syntax here is, and I'll explain these little apostrophes in a moment, the first value that goes in here, n, is the sample size. So n is the sample size. P is the population proportion, and S is the number of samples. So what we're doing is, if I was to do this with one sample of 10, I would get a series of zeros and ones, and then we can count up the number of ones, which constitute successes, divided by the sample size, and that will give us a sample proportion. So that's why it's been divided by the sample size there. So if you look in cell A1, that 0.8 tells us that in this sample of 10, we found that 8 of the sample of 10 were right-handed and 2 left-handed. That's what we see there. These apostrophes are indicating that N, P and S are called variables. And the reason why variables need to be demarcated, or they're called variable references, the reason why they need to be demarcated from cell references or column references is we have columns in the spreadsheet that are labelled N and P and S. So if I was to put this formula into this formula cell and just wrote it out as it is, it would ask me about N, P and S. And my answer to the dialog box questions would be, I want them to be variable references. And once you answer that question, as a result of answering that question, you get these apostrophes. Now, I've got N, P and S stored as values, and these are stored on the right-hand side of this page, and it's in a notes page. So if I press Control-Tab, I've now got my notes page is live, and so if I click on sample size there, see how I've got a math box there. Now in blue, I've assigned N to be 10, so that's the sample size, and the green bit is the output, which is 10. So if I get out of that, the other thing that I've done there, folks, actually, is if I press Control Menu, which is a right click on the PC, number 8 for MathBox Attributes, I have chosen to hide the input. Right? So there you can have your math boxes looking differently. You can hide input, show input and output, hide output, no calculation, etc., etc. So if I hide input still, okay. Here's our population proportion, which is P. Here is the samples, number of samples, which is 200. I've also put in math boxes for the mean. So this is currently the mean of all the sample proportions, 0.6495. That's not too far away from 0.67, and we would conjecture that if you increase the sample size, that would get even better. Here we've also got the standard deviation for all the proportions, and that's 0.16805. And as we increase the sample size, we would expect that to get closer and closer to that quantity, the square root of P by 1 minus P all over N. So that's how we would, that's a setup of the page. And let's see now what happens when we do this simulation. If we go to the next page, here is a dot plot which illustrates all the samples. So there's 200 dots there. There's 200 samples of size 10. And you can see that it's possible to get 3 samples where they're all right-handers. Here's 2 samples where there's only 2 right-handers. And you can see, if you have a look at it, I would ask the students, well, is there a skew? Now, because we're sampling and we're assuming that P is 0.67, there's a skew to the left. It does look a little bit normal, with a lot of samples around 0.6 and around 0.7, less so at 0.5 and 0.8, etc., etc. And you'll also notice that there are 2 vertical lines on the screen. One represents the population mean. So if I click on that, the population mean there is 0.67. And the other one represents the mean of all the sample proportions, 0.6495. So we would expect that if we increase the sample size, those 2 lines should get closer and closer together to the point where one would superimpose over the top of the other. So a question begs, how do you insert one of these vertical lines? Well, what you can do is you can press Menu, you can go to number 4 for Actions, number 8 for Plot Value. And the reason why V3 comes up here is because V1 has already been taken up with the mean of proportion of right-handers, and V2 has already been taken up by typing in P. So, for example, if I wanted the population proportion, I would type in P and press Enter. Notice that that P is bold and non-italicized, which means that P means something on this page. It has a value for it. If I wanted the mean of the sample proportions, mean, open bracket, and then if I pressed var, which is short for variable, there I would find prop RH. I'd paste that in, press enter. So that's how you insert or graph, if you like, a vertical line. That's plot value. Okay, if we go to the next page, here it is represented as a histogram, and we can see there that it's looking approximately normal, and I have put a show normal PDF curve over the top of the histogram, so it's superimposed over the top of the histogram. If I click on this normal curve, it gives us some fantastic information. It gives us the sample, the mean of the sample proportions, and it also gives us the standard deviation of the sample proportions. So that's really good knowledge to have. They were actually published back a couple of pages ago in that notes page. If We go back to page 1.2 and click in there on cell A1, you can continue to generate sample after sample with a shortcut. If you press Control R, see how we've got a new set of samples. I know you can only see it for the first 5 cells there, but Control R, the R stands for refresh or repeat. You can continually obtain 200 samples of size 10 over and over and over again. We will get, this is really interesting, we get a new dot plot, and look at the mean of the sample proportions and the population proportion. They're superimposed over the top of each other. And that's borne out by here. The mean of the sample proportions is 0.6735, and the standard deviation in this instance is 0.144, etc. So that's pretty good. Let's go now and let's change the sample size. Let's change the sample size to 30. Let's make it bigger. In our minds should be the fact that we should get less spread. The mean of the sample proportions should be a lot closer to the population proportion. In fact, the distribution should be behaving more and more normally. So if we press enter, so this 0.7 here, this represents 21 right-handers out of 30. So let's see how we go with our conjectures. We go to page 1.3. Fantastic. We see that it is scrunched up more. Okay. There is a slight difference between mean of sample proportions and the population proportions. No problems. That's what we expect. And also note, folks, that when you come to increase the sample size, there's a very good chance that you'll need to change the window here. You need to change the frequency. So I won't actually do it, but Control menu in open space and then zoom and window settings, that will enable you to change the frequency. I'm not overly worried about the histogram here. But if I now go to 1.5, what we've, and understand that I would do this in a lot slower fashion with the students, and in fact I would start with some really, really small values of n. You know, I might do n equals 2, n equals 5, n equals 10, n equals 15, n equals 30, n equals 50, 100. I'm just really condensing it here to give you a feel for what you might do. What we're really dealing with here is that when the sample size increases, and usually textbooks will say n greater than or equal to 30, and they'll also put a condition on that the product of n and p and the product of np1 minus p, some textbooks will say both have to be greater than 5, some textbooks will say both have to be greater than 10. But when that's the case, the distribution of the sample proportions, which is capital P hat, has an approximately normal distribution with a mean given by P, the population proportion, and the standard deviation sigma, which is given by the square root of P by 1 minus P on N. So that n's in the denominator there. You increase N, and you decrease the spread, and we saw that. So I think that with teaching statistics, you have to convince the students, and the way to convince the students is by simulation. And if you can simulate well, I think that they will end up with a good conceptual understanding derivation I gave using expectation algebra. Notice here that this is another notes page. That's the mean of the proportion of right-handers. That's the standard deviation of the sample, and notice that that's really getting quite close to sigma there. And so as we increase n, these two values get closer and closer together. Okay. Now, I want to finish off by showing you a couple of questions that students can do in the exam, and doing it using the notes page should ensure that as long as they understand what the question is asking of them. I know that that's a caveat, but as long as they understand, they know what the question is asking, I think that they can do these questions very, very quickly. They can get them right, and they can move on to more challenging problems. Now, the 95% confidence interval, or the approximate one for P, the command that you have to dig out is called the 1 proportion Z interval. Okay. Now, I've got a notes page here, so just to show you where that comes from in the notes page, if I press menu, I go to calculations number 6, I go to statistics number 6, and then confidence intervals number 6. It's a bit of a devil of a command to dig out. And then thank goodness it's not another number 6, it's number 5 for 1 proportional Z interval. That's the command that you would dig out, that one there. If you were to do this on a calculator application, it's very similar. You'd go through statistics, confidence intervals, etc., etc. I did that more just to prove really that in a math box you can do everything that you can do really on a calculator application except run programs, I think. So using the sample proportion from one sample, little p hat, what we're going to do is calculate an interval that we're 95% certain contains the population proportion. So this is a lot more realistic. The population proportion is not known. And so a survey found that 350 out of 500 people considered themselves as right-handed. Find an approximate 95% confidence interval for the proportion of people who consider themselves as right-handed. So we're not considering ambidextrous people here. They're either right-handed or they're left-handed. And what we can do is we can set up notes pages, and I've put a very provocative heading there. It says student access in exam. So in other words, students, teachers, myself, Russell, whoever has got some clues with Nspire, can make these notes pages. They can save them. They can bring them into the exam. They can. There's unfettered access to them, and it's up to the examiners then to recognise that they exist and to ask questions which continually test the cohort. So I've got some text here. It's prompting text, number of successes, sample size, confidence interval. These are math boxes. These math boxes correspond to the dialog box architecture that you see when you call up the 1 proportion Z interval command. So here the number of successes is 350. The sample size is 500. The confidence level, this is confidence level, is 0.95. Right, so confidence level is measured out of 100%. 95% is usually the one that's used. And here is a math box of results for that X, N and CI value. And what you'll see is that we're 95% certain that the population proportion lies between 0.66 and 0.74. Notice that there is a statistic here called margin of error, 0.04. And what that margin of error is illustrating really is it's the amount of random sampling error in a survey's results. And I like to think of it as a radius or half the width of a confidence interval. The larger the margin of error, the less confidence one would have in the results. And you can tell that if you calculated p hat minus the margin of error, you would get the lower endpoint of the confidence interval, and similarly p hat plus the margin of error gives you the upper endpoint. So why bother making something like this? Well, let's say the student's got a question where the sample results suggested that there were 300 successes and the sample size was 400. You get an automatic update on the results. There we go. Our 95% confidence interval is between 0.71 and 0.79. We're 95% certain that the population proportion lies between those two values given the sampling that we just did. given the results of that one sample. And finally, I'm about 3 or 4 minutes away, Rodney. So finally, if we look at precision and margin of error, I think a common sort of exam question, although I'm not part of the VCAA, might be finding the sample size given a margin of error. So here's quite a wordy question, I must admit. Determine the sample size required to achieve a margin of error of 2% in an approximate 95% confidence interval for the proportion P of people in Victoria who consider themselves as right-handed if the sample proportion is or was found to be 0.7. And we can set up another notes page which deals with this. Again, a provocative heading, student access in the exam. Using these math boxes, Control M, for example, if I just went in here, just to remind you, Control M, that opens up a math box. I type in ME, and there we go. So I've assigned the margin of error to be 2%, P hat is 0.7, and the confidence, I should change that actually to confidence level CL. I'll change that and resend it when you download it. That should be CL. I might change it now actually. CL 0.95 and then change this to CL. And that should be all right. So now all we need to do is solve the equation for the margin of error equals the inverse normal of 1 plus the confidence level divided by 2 multiplied by P hat by 1 minus P hat all over N. And what you'll find is this wonderful result that to achieve a margin of error of 2%, you only need to poll 2,017 people, which is quite outstanding. The reason why I've used this here in the formula, I've been a bit fancy. Most of the time students will deal with 95% confidence intervals, and if you appeal to the shape of the normal distribution curve, that really corresponds to an inverse normal of 0.975. In other words, 1 plus 0.95 all divided by 2. Okay, so that's where that comes from. So that's a little bit of smarty pants stuff from me. But just to give you a sense of the way that Newspoll and other such pollsters work, if you had 96 people, your margin of error is going to be about 10%. If you had a sample size of 384, the margin of error is 5%. If you had a sample size of 600, the margin of error is 4%. 1,067 people, the margin of error is 3%, etc., etc. So it gives you an idea of how pollsters scientifically work out the size of their sampling so that they can offer results to a particular margin of error. So I think that talking about Newspoll and the like would be really, really good as a teaching activity and a discussion and a use for really what they're doing. So I think that that's all I wanted to talk about. Russell, did you want to say anything in conclusion?
Probably not, Peter. You've done a very, very good job there. One of the things, some of the participants will notice the use of the word standard error instead of standard deviation when we're with regard to sampling proportions. They're basically interchangeable. So don't panic if you see standard error as being used for standard deviation. Other than that, I think you've addressed it very, very well. It will bring back memories to some of the more experienced, i.e. older teachers who taught reasoning and data extensions, a lot of this inferential statistics. So it may be a wake-up call to some people to say retirement might be a bad idea. Thanks for that, Peter.
And on that note, it's goodbye from Stadler and Waldorf, and it's over to you, Rodney.
Well, thank you, Peter. Thank you, Russell, for a wonderful webinar. You showed many hints and tips that proved valuable for teachers. It was a wonderful presentation. Now, to all viewers, remember your feedback's important, so please take the time to complete a brief survey at the conclusion of this webinar. This helps in the planning and presentation of future webinars. Speaking of webinars, To view or online or download webinars, visit the Texas Instruments Australia website, which I have in front of you. And if you see in the middle of the web page, there's the webinars. If you click there, up will come the next page, and you'll see that they have the upcoming webinars, as we have the busy day today. And there's also the on-demand tab. Now, there's a list of upcoming webinars, as I've just said. The program for the rest of the year has been set, and more webinars will be listed soon on this upcoming webinars tab. If you click on the on-demand tab, you'll see that you can actually play the webinar online, or you can download it and save it to your hard drives. And then you can also download associated documents like TNS files, PDFs as you saw today. So in a few days' time, you'll get your email and link to the resources and your webinar certificates. So it's all coming to you in a few days. So thank you for viewing the webinar, and until next time, take care.